When dealing with 5 kilovolts cable turns in rigid conduit, there isn't a specific code requirement that differs from the general code applicable to installations of 600 volts or higher concerning the bend radius. The important thing is adhering to safe practices. A general guideline to follow is to ensure the bend radius is at least 20 times the cable's diameter. This helps prevent damage to the cable's insulation during installation and over its operational life. Also, it's important to provide adequate support for the conduit system to avoid sagging, which can stress the cable. When making turns, use sweeping bends to prevent sharp angles, which could also damage the cable or reduce its lifespan. Now, let's talk about manholes. The code doesn't specify a required distance between manholes. The decision on spacing needs to consider practical aspects, such as the length of the cable sections being installed, the size of the conduits used, and how accessible the system will be for future maintenance. Considering these factors will optimize the design for both installation and long-term operation. Regarding whether you need a manhole at every right or left turn, the code doesn't mandate this. However, strategically placing manholes at critical turns or in locations where access might be needed in the future for maintenance or repairs is a good idea. This proactive approach can save time and resources if modifications or repairs are necessary later on. Moving on to grounding, it is highly recommended to run a continuous ground wire from the main outdoor switch, with a 4160 volt service enters to all subsequent outdoor switches and transformers throughout the complex. Implementing a continuous ground wire establishes a common ground reference, which minimizes the risk of ground loops. Ground loops can lead to unwanted current flow, potentially causing interference or even posing safety hazards. While it is technically feasible to have separate grounding systems for each building, it is generally not the best practice. A common, interconnected ground system offers enhanced protection against electrical faults and surges. By tying all grounds together, you create a more robust and reliable safety net for the entire electrical system. To elaborate further on cable bends, think about the physics involved. When you bend a cable too sharply, you are compressing the inner radius of the bend and stretching the outer radius. This distortion can weaken the cable's insulation, making it more susceptible to break down over time, especially under high voltage stress. That's why the 20 times the cable diameter rule of thumb exists. It's a practical compromise between minimizing space and ensuring long-term reliability. When selecting conduit supports, consider the weight of the cable and the conduit itself, especially when filled with water or condensation. Support should be spaced closely enough to prevent the conduit from sagging excessively between supports. Sagging can put undue stress on the cable, particularly at the bends, and can also create low spots where moisture can accumulate. Planning the layout of manholes requires balancing cost, convenience, and future needs. Fewer manholes might save on initial construction costs, but could significantly increase the difficulty and expense of future maintenance or repairs. Consider the types of equipment that might need to be installed or replaced in the future and ensure that the manhole locations provide adequate access for these tasks. The decision to use a continuous ground wire versus separate building grounds often comes down to a trade-off between cost and performance. While separate grounds might seem simpler to install initially, they can create potential problems if not properly coordinated. Differences in ground potential between buildings can lead to circulating currents and interconnected metallic pathways, such as communication cables or metallic water pipes. These circulating currents can cause interference, corrosion, and even pose a shock hazard. A continuous ground wire, properly sized and installed, helps to equalize ground potential across the entire complex, minimizing these risks. The size of the ground wire is crucial. It needs to be large enough to safely carry fault currents back to the source, allowing protective devices such as circuit breakers or fuses to operate quickly and clear the fault. Consult the National Electrical Code, specifically Table 250.122, to determine the appropriate size of the ground wire based on the size of the overcurrent protection device in the circuit. When installing the ground wire, make sure to use proper bonding techniques at each connection point. This means cleaning the surfaces of the conductors to remove any oxidation or corrosion, and using appropriate connectors that are listed for grounding purposes. Also torque the connectors to the manufacturer's specifications to ensure a reliable and low resistance connection. Consider using exothermic welding, also known as a cat weld, for critical grounding connections. Exothermic welding creates a permanent, molecular bond between the conductors, eliminating the risk of loose connections or corrosion over time. This is especially important in underground installations where the connections are exposed to moisture and other corrosive elements. Remember to document the entire grounding system thoroughly, including the size and location of all ground wires, connections, and grounding electrodes. This documentation will be invaluable for future maintenance and troubleshooting. In addition to a continuous ground wire, consider installing supplemental grounding electrodes at each building. These electrodes, typically ground rods or ground plates, provide an additional path for fault current to flow to earth, further reducing the risk of electrical shock. When selecting grounding electrodes, consider the soil conditions at the site. Soil resistivity can vary widely depending on the type of soil, moisture content, and temperature. Low soil resistivity is desirable, as it allows fault current to flow more easily to ground. If the soil resistivity is high, you may need to install multiple grounding electrodes in parallel to achieve an acceptable grounding resistance. Consult with a qualified electrical engineer to determine the appropriate grounding system for your specific application. They can perform soil resistivity testing, calculate fault currents, and design a grounding system that meets all applicable codes and standards. Consider the impact of lightning strikes on the grounding system. Lightning can induce high voltage surges on electrical systems, which can damage equipment and pose a safety hazard. A properly designed grounding system can help to mitigate the effects of lightning strikes by providing a low impedance path for the surge current to flow to ground. Consider installing surge protective devices, or SPDs, at the main service entrance and at critical equipment locations. SPD are designed to clamp voltage surges and divert the excess current to ground, protecting sensitive electronic equipment from damage. When working with 5 kilovolt systems, always follow safe work practices. Wear appropriate personal protective equipment, including insulated gloves, safety glasses, and flame-resistant clothing. De-energize and lock out the equipment before working on it, and verify that it is de-energized using a voltage tester. Be aware of the potential for arc flash, which is a dangerous electrical explosion that can occur when working on energized equipment. Perform an arc flash hazard analysis to determine the appropriate level of personal protective equipment required for the task. Remember that electrical codes and standards are constantly evolving. Stay up to date on the latest requirements by attending training courses, reading industry publications, and consulting with qualified electrical professionals. By following these guidelines, you can ensure the safe and reliable operation of your 5 kilovolts electrical system. It is important to always consult with a qualified engineer when designing electrical systems that are 600 volts and over. Furthermore, grounding is a critical aspect of electrical safety. The purpose of grounding is to provide a low impedance path for fault current to flow back to the source, which causes the overcurrent protective devices like circuit breakers or fuses to trip. This quickly de-energizes the faulted circuit, preventing electrical shock and minimizing equipment damage. Grounding also helps to stabilize voltage during normal operation, preventing voltage fluctuations that can damage sensitive electronic equipment. The grounding system typically consists of a grounding electrode, which is a metal rod or plate buried in the earth, a grounding electrode conductor, which connects the grounding electrode to the electrical system, and a bonding jumper, which connects all non-current carrying metal parts of the electrical system together. These parts include the metal enclosures of equipment, conduit, and cable trays. Bonding ensures that all these metal parts are at the same electrical potential, minimizing the risk of electrical shock. The size of the grounding electrode conductor and the bonding jumpers is determined by the size of the service entrance conductors. See the National Electrical Code Table 250.66 for grounding electrode conductor sizing and Table 250.102 for bonding jumper sizing. The grounding electrode must be installed in accordance with the National Electrical Code requirement. It must be located as close as practical to the service entrance and must be buried deep enough to ensure that it is in contact with permanently moist soil. The grounding electrode conductor must be securely connected to the grounding electrode using approved connectors. When running a continuous ground wire, make sure to size it appropriately for the available fault current. A smaller ground wire is suitable for general grounding purposes, but not for fault current return. Table 250.122 of the National Electric Code specifies the minimum size of equipment grounding conductors based on the rating of the overcurrent protection device. Remember to check local codes and regulations, as they may have additional requirements for grounding systems. Utility companies often have specific grounding requirements for their equipment. Always consult with the local utility company before installing or modifying a grounding system. Proper grounding is not just a matter of code compliance, it is a fundamental safety requirement. A well-designed and properly installed grounding system can save lives and prevent property damage. Don't take shortcuts or cut corners when it comes to grounding. Always follow best practices and consult with qualified electrical professionals to ensure that your electrical system is safe and reliable. In conclusion, when working with medium voltage systems such as 5 kilovolts, pay close attention to the details of cable bending, manhole placement, and grounding. These are critical factors in ensuring the safety and reliability of the electrical system. A proper grounding system should be tested periodically to verify its effectiveness. Ground resistance testing can be performed using a ground resistance meter. This test measures the resistance of the grounding system to earth. The resistance should be low enough to allow fault current to flow easily to ground. If the resistance is too high, the grounding system may need to be improved by adding additional grounding electrodes or improving the connections. Visual inspections of the grounding system should also be performed regularly. Check for loose connections, corrosion, and any other signs of damage. Repair any problems immediately to maintain the integrity of the grounding system. Make sure all the connections are properly torqued.